In this video, I'm going to be reviewing how to predict the products of a chemical reaction. And in order to do that, there's several things that you have to know beforehand. And if you don't remember these, you probably need to go back and review them. The first is the type of chemical reaction that you're dealing with. So when they give you a problem, the very first thing you have to do is recognize which of these 5 basic types that reaction is. You have a synthesis, which you're looking for only one product, a decomposition, where you're looking for multiple products but only a single reactant. Combustion is generally hydrocarbon combustion, and the reactant will be combining with oxygen, and you're always going to get carbon dioxide and water. Now there are other types of combustion reactions, but right now we're just going to label hydrocarbon reactions with oxygen as combustion. There's a single replacement reaction where you have a single element that's replacing one in a bond, and a double replacement reaction, which is where you have two usually ionic compounds that are switching partners. So if you're a little shaky on how to identify the types of chemical reactions, you probably need to practice that before going any further. Now the second thing you might want to recall are these symbols that are used when you write chemical equations. Each one has a specific meaning and is a clue that will help you predict the product. And we're going to be using these when we write these equations. So here are some problems, some 5 basic problems that you might see on a quiz or a test or in some practice sections of a book. And we're going to take these one at a time and write a balanced chemical equation for them. So on the next slide is the first one. Magnesium reacts with air. Well, it's going to be helpful for you to know what is in air, and hopefully at this point in your science education you know that air is approximately 20% oxygen gas and 80% nitrogen gas. Now there are some other trace gases, and that's not exactly 20% and that's not exactly 80%, but for our general purposes it's just easier to round them to those two values. So in air, these are the majority of your components right here that magnesium has to react with. So in this case you have a pure element that can react with another pure element of oxygen gas or this pure nitrogen gas. And I say pure, I know they're in a mixture, but when magnesium reacts with them, magnesium will react with the oxygen and it will also react with the nitrogen. So when you're looking at two elements combining, generally speaking, you are going to have a synthesis reaction. So I'm going to write my formula for magnesium. Magnesium is a metal and can stand alone. Magnesium is a solid, as hopefully you have seen by placing magnesium strips into various acids. Hopefully you've done that in the lab. So this is magnesium metal reacting. We're going to first react it with oxygen gas. Assume that it will combine with O2 in the air. Remember, O2 is a gas, so I'm putting a little G at the bottom. Now in order to get this to happen rather quickly, in the laboratory you would take a piece of magnesium metal and simply hold it in the flame of a Bunsen burner, and it would immediately react with air. So that flame is providing energy for this reaction to occur, which means I have to put this triangle sign above my arrow. Now if you go back to the other slide, you can see that this triangle right here means that heat is applied to the reactants, and that's what's making or providing the energy for your reaction to occur rapidly. So when that happens, you're going to get magnesium oxide. Magnesium, if you look on your periodic table, it is an alkaline earth metal in column 2, and that means that it's going to have a positive 2 charge when it bonds. And oxygen you should know that it is in column 6 over there on the right, or column 16 of the periodic table. It's going to have a -2 charge when it combines. Therefore, I only need 1 magnesium and 1 oxygen. Now, one thing that you have to understand is that over here on the left side, whatever subscripts you have, they don't automatically go to the right side. These elements over here will combine according to their valence electrons. So magnesium has 2 valence electrons. It's going to give those 2 away. Oxygen has 6 valence electrons. It's going to gain those 2 from magnesium. When this exchange of electrons occurs, magnesium will be +2 and oxygen will be -2, which means you only need 1 of each. 1 magnesium and 1 oxygen. So what about this 2 over here? Well, that's why you balance the equation. Because there's this 2 over here, that's just the way oxygen exists in its pure form, it's diatomic. You can't go and put a 2 down here. That would indicate that 2 oxygens are needed for every 1 magnesium, and that's not the case. You can see that by their charge, it's just 1 to 1. So that means I'm going to have to put that big 2 in front of that compound. And that big coefficient multiplies both the magnesium and the oxygen by 2. So that means I'm going to have to go back to the left side and put a 2 in front of the magnesium. Now, my equation is balanced on both sides. The most common mistake students make when they are writing equations where they have to predict the product is they want to take these subscripts right here and just automatically move them to the right side, and you cannot do that. You must look at the valence electrons for the elements that are combining and write their formula based on their valence charge. Okay, let's go to the next problem. Alright, here I've got methanol, and it's burning. So that should be an indication that I have burning should mean combustion to you. Anytime you hear the word burning, you should think, okay, I'm combining with oxygen. I have combustion. So let's see. Methanol, it's a hydrocarbon. If you know from your nomenclature chapters that meth right here, that prefix means 1 carbon. Methanol, okay, this OL means that a group has been put onto the carbon other than hydrogen. You can think of it as starting out as methane, which means you would have CH4, and it looks like this. And I know this is a review. You should already be familiar with this. Okay, so this is CH4, this is methane. Methanol means that one of those hydrogens right there has been replaced. And it's been replaced, instead of just that H, it has been replaced with an OH group. Hence methanol. So essentially, you're going to have CH3OH as the formula for methanol. And you add, it burns, so you're adding oxygen to it. And by the way, methanol is a flammable liquid. It's the gas that's burning. Oxygen is a diatomic gas, so we're putting little G's down there. And as you know, anything that burns is going to need a little bit of activation energy from a flame or electrical charge to get this reaction going. Now, since it's a combustion of a hydrocarbon, you're always going to get carbon dioxide, gas, and water vapor. Technically, you're going to get some carbon monoxide as well, but we're going to leave that out of our equation because it makes it a little more difficult to balance sometimes. So in this course, we're going to assume that this is completely changed into carbon dioxide and water vapor. And it doesn't matter what hydrocarbon you start with. You always are going to get carbon dioxide and water. So now you just have to make sure that this thing is balanced. Use a different color for balancing. I've got one carbon on both sides. I have 4 hydrogen and only 2 hydrogen here. So if I put a 2 in front of that, that's going to make my 4 hydrogen. I'm going to go ahead and do that, even though I might have to erase it. But that 2 also goes to the oxygen. And this 2 oxygen here and the 2 oxygen here gives me 4. Over here I have 2 plus 1 is 3. This guy right here is making this oxygen come out to be an odd number. So I'm going to double this. When this occurs, when you have an odd man out, it's what I call just an odd guy making the whole total on one side odd, double the odd guy to make him even. So that means instead of the 2 over here, I'm going to have to put another number. So now I have 2 times 3 is 6, plus 2 times 1 is 2, so I have 8 hydrogen over here, which means this is going to have to be a 4. And I have 2 of the carbon, so I'm going to have 2 carbon over here. Now we can deal with our oxygen. So 2 times 2 is 4, plus another 4 oxygen is a total of 8 oxygen on this side. I'm just going to write it right up here. So I have 8 oxygen over here. On this side I have 2 times 1 is 2, plus 2 is 4 oxygen. So the only thing I can do is put something in front of this O2 that I can multiply it times 2 and add it to these 2 oxygen over here to make 8. So I'm going to say 8, because I want a total of 8 over here, 8 oxygen over here. So I'll say 8 minus these 2 oxygen here is a 6. So what can I multiply 2 by to get 6? And that's a 3. Now this equation was a little bit difficult to balance because you have to take into consideration that your oxygen is split on both sides. It's in 2 compounds here and 2 compounds on the product side as well. Alright, let's go to the next slide. Alright, here we have, as indicated by our activity series over here, if you remember your types of reactions and why we use an activity series, you'll know that we're talking about a single replacement reaction. And I should be using white because single replacement I've designated as white, or really a light blue. Alright, so here we got single replacement. Because here's your single metal, right there, there's your single guy, and it's placed into a solution of silver nitrate, that's a compound. So this copper metal is going to kick out the silver out of this compound. And the reason you know that is because copper is positive 2. When it's fully oxidized, it's positive 2. And silver is positive 1. So the positive is going to replace a positive and bond with the negative. Now in order to do that, this nitrate right here, it must be more attracted to the copper than it is to the silver. And that's what our activity series is for. So we look on our activity series and we find silver. Silver is right here. And then we look for copper. Copper is right there. So you can see copper is slightly above silver in the series. That means it's more reactive. And because copper is more reactive than silver, that means that nitrate will be more attracted to it. And that's important because if your single metal is not the most reactive, you won't have anything happen. So this single element must be more reactive than the element it is replacing. In this case, silver. If it's not more reactive than the element it is replacing, no reaction will occur. But in this case it is. It's higher on the activity series, so it's more reactive. And we can go ahead and write the equation. So I have copper metal, which means it's a solid, plus silver nitrate. Silver's +1, nitrate is -1. So I have a 1-to-1 ratio of those ions in the compound. They are in aqueous solution. And so this copper is going to kick out the silver and bond with the nitrate. And you have to use the highest oxidized form of copper, which is +2. So that means you're going to have a ratio of 2 of the nitrates to 1 of the copper. Copper in its highest oxidized form is +2. Nitrate is always -1. So that means I need 2 nitrates for every 1 copper. And then that is going to be, the symbol down here is going to be AQ. And then that's going to leave silver. And the silver by itself is going to be a solid. I don't know if you can see that. But the silver is going to precipitate out. If you were to actually do this in the lab, you would have a clear solution of silver nitrate, and into it you could put like a piece of copper wire or a copper strip, and as soon as you started putting it, you placed in that solution, little tiny silver ions would start to come out of solution and form silver metal. Essentially what's happening is some of these electrons from copper are being given back to silver, so that it comes out of solution as a solid and it precipitates, and you could see this very fine shiny silver particle start to form on the outside of that copper. And at the same time the copper is going to go into solution as an ion. So now in this equation all we have to do is balance it. So I have 2 nitrates over here, that means I need 2 over there, and that changes my silver, so I'm going to put a 2 in front of it. Now when you have a precipitate, one thing you have to understand is that it requires a net ionic equation. A net ionic equation is another chemical equation that shows the ions that are changing, only the substances that are changing. And you do that when you have something going to a solid, when you have some sort of precipitation. So right here I can put on this side just the ions that are interacting, and that means that this copper here is going from a solid into an ion, so I'm going to include that, and the silver is going from an ion into a solid. What happens to the nitrate? Nothing. It stays NO3. It stays dissolved. So you don't include that in your net ionic equation. So all I do is on this side I write copper solid plus what's changing here? Not the nitrate, just the silver ion. And what am I getting? I'm getting this copper ion. Remember, it's going to be fully oxidized, so that's copper +2. Oops, and I forgot to put my little AQ symbols here too. And I'm left with this solid silver. Now you have to make sure that your net ionic equations are balanced by mass and balanced by charge. Right now I have this silver over here, but it only has a +1 charge, and this copper has a +2 charge. So that means I need to put a 2 in front of it so that I have +2 on this side as well. And so that means that my silver by mass is out of balance, so I need to put a 2 over here. Essentially, it's the same thing as up here. You've just left the nitrate out because the nitrate's not doing anything. It's just sitting there. It's spectating. We call the nitrate a spectator ion because it is not reacting. It's just watching kind of what happens to between this copper and silver, what interaction is happening between those two. And that's what we write in the net ionic equation. Okay, let's go to the next one. Potassium chlorate. Okay, potassium chlorate is heated. So that's the only thing you're given here. One compound and you're heating it up. right then and there you should think, okay, I have one thing, what possibly can happen if I heat this one thing up? Well, it's already a compound, so it's probably not going to interact with anything in the air. It's going to split apart. And in this case, you're going to have a decomposition reaction. So we're looking at that one right there, decomposition, because there's only one thing. And when you heat a compound, it's going to decompose. So I have to write the formula for potassium chlorate. Chlorate ClO3, it's got a -1 charge. Potassium is a +1 charge. And this is a white ionic solid. It's a powder. And it says it's heated, so I need my little triangle. Now, there are 5 basic decomposition reactions that you're just going to have to memorize. And I will list them for you on the next slide in case you've missed that information somewhere along the way. This is one of them. This is the decomposition of a chlorate. When a chlorate decomposes, you always get the same thing no matter what metal chlorate you start out with. You're going to get the metal chloride. So the metal here is potassium chloride. Potassium is +1, chlorine is -1, so that's 1 to 1. It's still going to be a solid. And what actually is happening here is when you heat this, you're driving off this oxygen. And you know that oxygen is always a diatomic compound when it's by itself. So when you heat this up, you're driving off that oxygen and you're leaving behind the metal chloride, and then there's that oxygen gas that's leaving. This happens anytime a metal chlorate decomposes or you heat a metal chlorate. The oxygen is going to leave as O2 and you're going to be left with the salt, the chloride salt of whatever metal you started with. Now we can balance this. You can see over here the only thing that's out of balance is the oxygen. You have a 3:2 ratio from one side to the next. So we're going to have to double that on the left side to make that even, because I've got to be able to multiply that 2 by something. So 2 times 3 is going to be 6, and then I can put the 3 there. When I put the 2 here, it changed the potassium and the chlorine, so I'm going to have to put the 2 there. And you can see this is a 2 to 2 to 3 ratio. You can't reduce it any further, and you're finished. Okay, I said I was going to put this information on the next slide, but I have room here, so I went ahead and put it in here. These are your basic decomposition reactions, and if you remember, decomposition is the reverse of synthesis. So if you can turn this arrow around the other way and imagine these things over here being your reactants and that being your product, then you have 5 basic types of synthesis reactions as well. So these are the things that if you have not seen them before and had a chance to commit them to memory, then you need to do that now. There are these 5 basic types of decomposition reactions. When chlorates break down, it doesn't matter if it's potassium chlorate, magnesium chlorate, iron chlorate, doesn't matter. You're always going to get the metal chloride and oxygen gas. Same thing for metal carbonates. You'll get the metal oxide and carbon dioxide. Metal hydroxides break down into metal oxides and water vapor. Binary salts simply split apart into their pure elements. Acids will split apart into a gas and then water. And you can also turn it back the other way and go into synthesis. Think about them that way. So you can come back and refer to this chart here over and over again if you need to. Now we're going on to the next reaction. Here we have some lead 2 nitrate and some potassium iodide in an aqueous solution. So right here, this is one compound. It's got a positive and negative part mixing with another compound with a positive and negative part. So you have 2 ionic compounds or ionic salts, and when they're mixed together in an aqueous solution, they're going to switch partners if they can. So this is double replacement. Let's change my pen color. All right, double replacement. So the first thing you're going to need to do is you can go ahead and write down the formulas for these two compounds. Lead 2 nitrate. Lead is a positive 2 charge in this compound, so that means I'm going to need 2 of them to go with this nitrate. Okay, I just wrote that wrong. Sometimes I'll do that accidentally. Alright, positive 2 here, negative 1 there, so I need 2 of those nitrates to balance the charge on the lead. And it said it was an aqueous solution, so I'm going to put my AQ. Plus potassium iodide. Potassium is positive 1, iodine is negative 1, so I need 1 of each. And they're both an aqueous solution. Don't need any heat for this reaction to occur. So let's see what we could get. These two guys right here are going to split apart because they're ions. You put them in water, they split apart, they dissociate. And the potassium and the iodine are going to split apart. And then that leaves them free to get shuffled around and switch partners if they're attracted to the other partner. So in this case, the positive part of this one, which is the potassium, is going, and sometimes it's helpful to write those charges above them so that you just remember what they are. So this positive potassium is going to hopefully be attracted to this negative nitrate, and you can get KNO3. I'm going to leave this state symbol off right now. And then this positive lead can be attracted to the negative iodide. Lead is positive 2, so that means I need 2 of those iodines to balance the charge on the lead. Now, here is where you have to consider solubility rules. Solubility rules are very important in determining if a reaction is really going to occur. Okay, and here's something else that you have to commit to memory. Now, I say you have to memorize it. You don't have to memorize it for Chemistry 1, but if you're going to go further into chemistry, if you're going to take AP Chemistry or a higher level inorganic chemistry class, you really have to have these memorized. So I've given you some solubility rules on the next slide, and we're going to use them to see if this one is going to stay soluble, which means dissolved in water, or if this one is going to stay soluble. Both of them might still remain dissolved in water. If they both are soluble, then you don't have a reaction occurring here. All you have is a big solution of ions. But if one of them is insoluble, that means it becomes a solid and it will precipitate out. Then you do have a reaction occurring. So let's go look at the chart. We've got to figure out if potassium nitrate will remain dissolved, or if the lead iodide will remain dissolved. So let's go to our rules. Ooh, there's a lot of rules here. We'll just go through them. We have an iodide and we have a nitrate. So that's, here we go. Here's some, Rule 2C deals with iodides. It says all iodides are soluble. That means all of them will remain dissolved except for ones of silver, mercury, and lead. So right here it tells you that lead iodide is insoluble. So now I know that I'm going to have a precipitate of lead iodide. But what about the potassium nitrate? Right here it says chlorates, nitrates, and acetates are soluble. They're always soluble. Nitrate, doesn't matter what's with a nitrate, it's always soluble. Always going to remain dissolved. So I can go back up here and I can put an AQ next to this potassium nitrate because it's still soluble. But this one right here, it was an exception. It said it precipitates out. So this is going to become a solid precipitate. Now when you have a solid precipitate, you're going to have to write another one of those net ionic equations for this reaction. Now, what is the net ionic equation concerned with? Just the thing that is new. This is new. Everything else, whoops, Everything else is remaining dissolved. So I need to write an equation for the formation of this lead 2 iodide. Where does it come from? It comes from this ion and this ion right there. So that's what I'm going to write down here for the net ionic equation. The lead 2 ion, and it was dissolved at first because it was with a nitrate. And the iodide ion, which was also dissolved in that potassium iodide compound. But when they get together, they form an insoluble substance. They form a solid. Whoops. Got my B. And so I'm going to balance this. I've got 2 iodines here. I need 2 there. And this is my net ionic equation. Alright, so remember, whenever you have a double replacement reaction, whenever you have that, you must consult your solubility rules to see if you were going to have a solid. Now, if this had not been a solid, if it had dissolved in water, then essentially I have no reaction. I just have a solution of ions that are floating around. But if I do, I must write a net ionic equation that illustrates the formation of that new substance. Now, I've given you the solubility rules on this slide. I can go ahead and take these off so it doesn't confuse you if you want to stop the video at some point. Well, I thought I was. I can just move it. And you can hopefully come back to this slide if you need it, because I have some practice problems over here for you to try. Now, there are 10 of them. There are a variety of types. I'm thinking I gave you one of each type, and of course some of them are going to be duplicated. And on the next slide are the answers. So try not to look at the next slide, or but I'll go until you're finished with this. So you can pause the tape here and try to do these on your own, and then I will put it to the next slide, and then you can see if you got it right or not. So now you can pause the tape. Hopefully you have gotten most all of these correct. So if you didn't, then my students will need to email me. If you are not one of my students, then you'll need to maybe go back through the video and watch it again. There's some other resources that you can find on YouTube as well. This is not the end-all video to help you with this problem or this area. I've just tried to give you guys some problems to practice on. Alright, that's it.